Welcome, everyone. So today we're jumping right into Chapter 11, setting the stage for what is honestly one of the absolutely most critical topics in software engineering. We're talking about availability and reliability. Look, our modern society literally runs on software 24/7. Because of that, we absolutely must be able to trust it to be available and reliable. If you've ever had an app completely crash on you at the worst possible moment, well, you already know exactly why this matters.
Here's our roadmap for this explainer. We'll start with an introduction to trusting software, then unpack the chain of failure. After that, we'll look at 3 approaches to reliability, compare reliability versus availability, discuss context and user perception, and wrap up with a lecture summary and your exam focus.
Okay, Part 1, Introduction to Trusting Software. We really need to anchor ourselves in what software actually does out there in the real world. Society relies on it 24 hours a day, 365 days a year. Think about it for a second. From life-saving medical equipment in hospitals to massive global banking networks to the systems controlling airplanes mid-flight, software just has to operate without crashing. It has to preserve our data and maintain our trust all day, every single day. If we can't trust the programs we write to behave exactly as we expect them to, the consequences can literally be catastrophic.
Moving right along to Part 2, the chain of failure.
Since we know just how heavily we rely on software, we have to understand microscopically how it actually breaks. To do this, we use a famous model by pioneer researcher Brian Randell. He gave us this incredibly precise 4-part sequence to deconstruct how failures happen. It goes like this: human mistake, leading to a system fault, which leads to a system error, and finally results in a system failure. Now, first-time students almost always mix these terms up, but in software engineering, they have very specific, distinct meanings. So let's walk through them step by step using a pretty relatable programming example.
Step 1 is the human mistake. The definition here is human behavior that results in the introduction of faults into a system. Imagine a programmer is writing code for a remote wilderness weather station, right? They make a simple logic error. They decide to calculate the next transmission time by simply adding 1 hour to the current time. But, oops, they completely forget that on a 24-hour clock, midnight resets to 0000. That human action, the typing out of that flawed logic, is the mistake.
Step 2 is the system fault. We define this as a characteristic of a software system that can lead to a system error. So, that mistake our programmer just made, it has now become a fault. This is the actual buggy code sitting silently inside the program. It's just hanging out there on the hard drive, totally dormant, waiting to be triggered. Step 3 is the system error. This is defined as an erroneous system state during execution that can lead to unexpected behavior. So now the program is actually running. The clock hits 2300, the buggy code executes, and it blindly adds 1 hour. Instead of properly resetting to midnight, the system calculates a time of 2400 or maybe even 2500. The program has now entered a bad internal state. That is your system error.
And finally, Step 4, the system failure. The definition is behavior that does not conform to the system specification or user expectations. This is the final stage. It's where the system actually crashes, or maybe it just completely fails to send the weather data. Either way, it ultimately fails to deliver the expected service to the end user. So, to recap, the human mistake created the fault caused the error, and the error broke the system.
Now here's kind of a fascinating twist. A system can actually have hidden faults that never ever cause a failure. You might be wondering, how is that possible? Well, first, the buggy code might just be dead code that is never executed by any user. It's there, but it's ignored. Second, errors can be transient. Maybe the system state gets overwritten by new, valid data before that bad data is ever even used. And third, you might have built-in protection mechanisms that catch the error and correct it silently behind the scenes, long before the user ever notices a thing.
Let's head into Part 3, 3 approaches to reliability.
All right, so now that we understand Randall's chain of failure, how do we as engineers actually minimize these issues in the real world? Well, we use 3 pragmatic engineering approaches. Number 1 is fault avoidance. This is all about preventing bugs in the first place, maybe by writing strongly typed code so that certain logic errors are just literally impossible to make. Number 2 is fault detection and correction. This is where we aggressively test and debug the program before deployment to catch whatever slipped through. And number 3 is fault tolerance. This means designing the system so that when errors inevitably happen at runtime, and they will, the system survives them instead of just crashing. But you might be thinking,
Why do we need all three? Why not just test the software until it's absolutely perfect? Honestly, it comes down to the economics of bugs. As you start removing faults, the cost to find those remaining, super rare faults rises exponentially. Finding the very last bug actually becomes economically impossible. At a certain point, it is far cheaper for a company to just release the software and design it to tolerate the occasional failure, rather than spending millions of dollars hunting down a bug that only happens, say, once every 10 years. Bottom line, 100% bug-free software is an economic myth.
Which brings us to part 4, reliability versus availability. Okay, this is really the climax of our explainer today. First-time students constantly confuse these two vital metrics, but they measure entirely different things. Let's define them super clearly. Reliability is the probability of failure-free operation over a specified time in a given environment. The crucial thing to remember here is that reliability focuses on whether the software is delivering correct, failure-free results over a continuous span of time.
Now, let's contrast that with availability. Availability is the probability that a system, at a point in time, will be operational and able to deliver services. Notice the difference? Availability doesn't care about a span of time. It simply asks, if I try to use this system right now, at this exact millisecond, is it up and running? Let's make this totally concrete with a practical, mathematical example. Imagine we have two systems. System A fails only once a year, but it takes 6 whole hours to fix. System B fails much more frequently, once a month, but it only takes 5 minutes to fix. Now, mathematically speaking, System A is far more reliable because it rarely fails. But look at the total downtime. System A has 360 minutes of downtime a year. System B? Only 60 minutes. Therefore, System B has much better availability. Depending on your business, like, say, a telephone switchboard, that incredibly quick recovery of System B might be exactly what you need.
Moving on to part 5. Context and user perception.
So we've looked at the math, but now we really have to look at the human element. Why? Because context dictates our perception of software dependability. Out of all the possible inputs to a system, only a tiny subset actually triggers errors, and different users have entirely different usage patterns. If an administrator uses the software quietly and predictably, they might never hit that erroneous subset. To them, the program is flawlessly reliable. But if you give that exact same software to a massive campus of students at Eduvos, they will inevitably click buttons in bizarre, completely unexpected combinations. Their usage pattern overlaps with those erroneous inputs, triggering entirely new subsets of failures. So keep this in mind. Reliability is highly dependent on the user's operational environment.
Finally, part 6, lecture summary and exam focus.
We've covered a ton of ground today, and you should hopefully now see that defining a failure is entirely subjective based on user expectations. Now, for your exam, here's exactly what you need to memorize. First, you absolutely must be able to differentiate the steps in Brian Randell's model. Know the distinct difference between a fault, an error, and a failure. Second, you must be able to define and mathematically contrast reliability versus availability. And third, make sure you understand that exponential cost curve that makes 100% bug-free software an economic impossibility. Which leaves us with one final, pretty provocative question. Knowing all of this, knowing that bugs are literally inevitable and users are completely unpredictable, how do we architect fault-tolerant systems based on these exact requirements? Think about how you would personally design a system to survive the very failures we just discussed. Keep that in mind because that is exactly what we'll be exploring in our next Software Engineering Explainer. Thank you so much for joining me, and keep learning.